second lecture in Module 8 on numerical solution of Navier-Stokes equations. In the previous lecture we had discussed the features of Navier-Stokes equations, and we also discussed some important points which we need to keep in mind in solution of compressible as well as incompressible Navier-Stokes equations. We would next discuss the application of explicit and implicit time integration schemes for Navier-Stokes equations, and then we would look at one family of methods which are called implicit pressure correction methods, which are widely used for solution of steady state problems. And we will also have a brief look at a family of methods called fractional step methods. So let us have a recap of what we discussed in the previous lecture. We discussed the special features of Navier-Stokes equation. Being a vector equation, it has got special properties. We have got flexibility with respect to the choice of the grid, and what does each choice mean? That is what we discussed in the previous lecture. We also discussed the mixed nature, and due to that what are the implications that we would rarely if ever use a steady state solution. We would rather try to obtain a steady state solution as an end result of an time dependent simulation. And we briefly discussed this special things which are involved in numerical simulation of incompressible fluids, in particular that there is no independent equation for pressure. So, we must find out we must derive a Poisson equation for pressure which would ensure the satisfaction of continuity. We also had a brief look at numerical simulation of compressible fluids, and we had brief conceptual outline as to how we can solve compressible flow problems, and what we saw that conceptually the simulation of compressible fluids appears to be a lot simpler, because here we have got independent equation for each variable. We have got continuity equation which represents transport equation for density, momentum equations as transport equation for velocity components, and energy equation as a transport equation for temperature or total energy. And we have got equation of state which supplies us the relationship between pressure, density and temperature. So, from which we can obtain pressure, and similarly we have got some certain constitutive equations which give us the material properties in terms of the flow variables. So, since everything is available which we require for the compressible flow, all the equations are available, and we have to just use a proper set of discretization techniques in a space and time to obtain our numerical solution. So, this is in stark contrast to incompressible fluids, where we had to contrive to derive an equation for pressure using both momentum and continuity equations. Now, in this lecture we would focus primarily on time integration techniques for Navier-Stokes equations. We would not discuss in detail about the spatial discretization used. So, we will presume our starting point would be what we call the semi-discrete system of equations, wherein we have applied our favorite spatial discretization scheme. It could be finite differences, finite volume or finite element method, and we have obtained a discrete algebraic equation in terms of time. And how do we integrate that equation? That would be the feature of focus of the lecture today. So, outline, we will have a brief look at numerical simulation of compressible fluids. We will have a look at one particular type of explicit integration scheme for compressible flows, and since it is an introductory course, we would not go into any further detail about the compressible flows, and you would be referred to appropriate references wherein you can find detailed algorithms for dealing with low speed as well as high speed compressible flows. We will focus mainly on numerical simulation of incompressible flows, and we will have a look at an explicit time integration procedure, then an implicit time integration procedure, and fraction step methods. So, now let us first have a look at numerical simulation of compressible flows. We had a look at the conceptual procedure in the last lecture. That is to say, what we have to do is we have to realize that continuity, momentum and the energy equations, they represent transport equations for density, free velocity components and the total energy. So, can we combine these into a generic vector transport equation. So that's what we will have a brief look at. So we'll combine these, and next this generic vector transport equation can be discretized using our choice of spatial discretization scheme, and then we can also apply a suitable discretization scheme in time to solve the flow variables, making use of the suitable equation of the state to take care of the pressure in momentum equation. And we would see that primitive variables, which are velocity components, density and temperature, they are obtained from our generic solution vector in this equation. And we will have one demonstration of this solution process based on an explicit scheme which is popularly referred to as McCormack method, which is essentially a predictor corrector method. So now let's switch over to a board and have a look at this solution of compressible flow problem. We would focus only on Navier-Stokes equations. There are many simplified cases in compressible flows. For instance, for very high speed flows, the effect of viscosity are negligible except close to the boundaries. So in that case, we might solve for Euler's equation, or if you are too far off and flow is irrotational, we can as well solve for the potential equation. So we are not going to deal with those equations. We would focus primarily on the most general case wherein the viscous effects are involved because of the presence of boundaries, and that is what we would focus on, our Navier-Stokes equations. So now let us first write down our equations the way we have learned them, or we have derived them earlier. So first our continuity equation, let us use the Cartesian tensor notation. So this is del rho by del t plus del over del xj of rho vj is equal to 0. Our momentum equation, del of rho vi over del t plus del over del xj of rho vi vj minus del p over del xi plus del tau ij over del xj, and suppose we ignore the source term or body force term, which could be combined with the pressure if you want to, or let's neglect for the time being. Similarly, we can write our energy equation, wherein we define, or we would write the equations for total energy, that is E is equal to our internal energy plus the kinetic energy is equal to our heat generation term minus the diffusion term P v I comma j tau I j v j comma I. The last two terms, they come because of what we call flow work, and Q is our heat flux vector. Now these three equations are in terms of what we call one variable is our density, the next variable is the 3 components of velocities. So, 4 plus our total energy 5, and we have got pressure 6. So, we have to supply a separate equation for pressure. So, for pressure we would have equation of state say we use ideal gas equation of state in some situations. So, P is equal to rho R T, and T could be obtained from our total energy E. If you know capital E, velocity and density, we should be able to calculate P and use that P in the solution of a momentum equation and so on. Now, let us define a new solution vector. So, let us define a vector of flow variables. Now, this would be, we are going to, let us use symbol capital U for this. This will contain the primary unknowns in each of these equations. So, primary unknowns are, let us say, density for the continuity equation. Momentum equations we have got, let us use Cartesian components, so rho u, rho v and rho w, and similarly the last equation we have got is rho capital E. Please be careful here, we have not used u, v, w and E, we have instead used the combination rho u, rho v, rho w and rho E, and getting the primitive variables u, v and E would be easier once we get the components. So, thus our solutions at primitive variables would be obtained as like u, that would be the second component of vector u. So, let us call it u2 by rho, or that is rho is u1, v is equal to u3 by rho, and w is equal to u4 by rho, and capital E would be u5 by rho. So, this capital U is a vector which has got 5 components, and in terms of U we can collect all these equations together. So, equations 1, 2 and 3 can be combined together into a single vector transport equation for the flow variable vector capital U, which we can write as del of U over del T plus del of F I over del x I plus del of g I over del x I is equal to a vector B. Well, now this F and J, they would, the del u by del T, that contains the collection of our time derivative terms. F will contain the convective terms. So, this is time derivative terms, convective terms and diffusive terms. This would contain all generation terms, generation or body force, source terms. For actual numerical implementation, what we can do is, instead of writing in generic form, let us choose Cartesian coordinate system, and in Cartesian coordinate system we can correct or rearrange the terms little differently. So, for numerical implementation, in Cartesian coordinates, let us rearrange. We will keep the derivatives of x, y and z separately. The above equation in terms of derivatives of x, y, z and t, and rewrite it as del of u by del t plus del a over del x plus del b over del y plus del c over del z is equal to zero. So, let us call this equation as our equation number 5. Now, here we can again rewrite in terms of ODE to enable us to apply the time integration schemes. So, we can put it as del u by del t is equal to minus of del a over del x plus del b over del y Now, we can use a suitable time integration scheme and a discretization procedure to solve this equation. Okay. So, in the context of finite differences, so let us choose our discretization procedure. Let us call it via finite differences for spatial derivatives and explicit time marching scheme. So, we can use one such thing, and one such a scheme is what we call McCormick method. Now, this McCormick method is a predictor corrector method. So, what do we do in first step of this method or predictor step? We would use the solution which is available at time t is equal to t n, that is a known time, to obtain a predicted value for the variable or our solution vector capital U. Use this predicted value again to update, let us say, our material properties and other terms, and thereafter thereby get a final solution which as an average of the predicted solution as well as the initial guess which we have, or initial solution at time t is equal to t n. So, here the first step is our predictor step. Okay. So, compute an estimate of flow vector U using forward Euler method. So, once you apply forward Euler method, we straightway get that our capital U at U, let us call it as U star. This at the grid point I j k is basically U at I j k at time level n minus delta t times now we have to use the special derivatives for A, B and C. So, let us substitute that, let us use forward differences for A, B, C's. So, A becomes A I plus 1 comma j comma k minus A I j k. This age vector age would be evaluated using the solution at time level n divided by delta x plus similarly B I j plus 1 k minus B I j k evaluated at time level n divided by delta y plus C I j k at n k plus 1 minus C I j k divided by delta z. So, this is a predicted value. Now, with this predicted value we would use in the corrector step. So, all these A, B's and C's, their components would be computed using this value U star, and solution would be obtained as a simple average of an Euler step value plus this predicted value. So, U at n plus 1 I j k, this would be given as an average of these two. So, 1 by 2 of U star I j k, which we have computed at the previous step, and if we use this U star I j k's for the evaluation of A, B, C's and start off with an initial condition at t is equal to t n, that is our U n. So, we get U at n I j k minus delta t times A star I plus 1 j k A star I j k divided by delta x plus B star I j plus 1k minus b I j k star divided by delta y plus c star I j k plus 1 minus c I j k star divided by delta z. So, now we have obtained our solution vector at the new time step at grid point I j k using an explicit scheme. And remember that this A star, B star and C star, they are the ones. So, this start values A star, B star, C star have been evaluated using U star. Now, remember this McCormack scheme is an explicit scheme. So, there are stability constants, and I would refer you to look into the books by Anderson, JD 1995 and Chung TJ 2010. These two books, the complete references are provided at the end of the lecture for further details. So, we are not going to discuss any further about compressible flows. We will now focus on the incompressible flow time integration schemes. Now, let us have a look at numerical simulation of incompressible flows. We have already seen that yes, in this case we need to derive a Pressure-Poisson equation to enforce the continuity. We can make use of an explicit time integration scheme. We can go for implicit time integration, or we can use a category of methods which are called fractional step methods. So, there are three which we are going to discuss in today's lecture, and this yet another category of method which is called implicit pressure correction methods, which we will discuss in the next lecture. Now, let us have a look at the characteristics of explicit time integration. Now, if we try and implement them, these Navier-Stokes solvers based on explicit time integration techniques, they are simplest to implement, because we can straightaway obtain the values of the flow variables in terms of the values at the preceding time instant. That is what we saw in the case of a McCormack method for compressible flows. The same way, here the velocity components could be directly obtained from our momentum equations in terms of the values at the previous time step. Okay. But this one problem here, that explicit time integration techniques, they have got severe stability constraints, and that puts or that imposes limitations on the time step which we can choose. So, explicit time integration schemes are recommended, or they are primarily used for the flow problems in which the accuracy requirements demand use of a very small time step. So, such would be the situations where, for instance, let us say we want the flow transient, something has happened suddenly, all of a sudden there is some disturbance in the flow field and we want to capture those flow transients, or if you want to perform a large area simulation or direct numerical simulation of turbulent flows. In each of these cases, we require a very accurate time history, and for this accurate time history, we should choose very small time steps, and this time step may be small enough to satisfy the stability conditions. So, these are three prime candidates in which we should prefer explicit time integration scheme, that is the problems involving flow transients and large eddy simulation and direct numerical simulation of turbulent flows. Now, let us see how do we obtain, or how does this explicit time integration scheme works. Let us have a schematic look at the algorithm and then we would summarize it. So, let us get back to our board. So, explicit Navier-Stokes solvers, and remember we are dealing with only incompressible flows. So, here most of the time you would be solving only the momentum equation, not the energy equation. Continuity equation would be used only as a kinematic constant. So, our primary focus would be on the solution of momentum equations. So, let us write our momentum equations. Del of rho V I over del T plus del over del x j of rho V I V j to minus del P over del x I plus del tau I j over del x j. For the time being, let us ignore the source terms. If they are present, they could always be combined together with the pressure. Now, we would like to apply a special discretization technique, and let us write the discretized equation. So, application of a special discretization technique, which could be finite difference, finite volume or finite element, it does not really matter. That will lead to a semi discrete system that would be discrete in space, but still continuous in time, semi discrete system given by rho V I over del T is equal to minus delta over delta x j rho V I V j minus delta P over delta x I plus delta over delta x j of tau I j. Now, here we have introduced this operator delta. So, as operator del over del x I represents spatial discretization operator, and it could be different for each term, that is for convective term, convective, diffusive and pressure term. See, what we would normally do is we would use central differencing. If you are dealing with finite difference or finite volume techniques, central differencing would be used for the pressure term and diffusive term, that is our stress term, and we would use some sort of an upwinding scheme for the convective term. Okay, so this was our convective term, this pressure term, and this is our diffusive term. Now, further, for the sake of notational convenience, we are going to introduce it and the short term notation. So, let this represent by H I. H I contains both our convective as well as diffusive terms. So, then we can rewrite 2 as del of rho V I over del T is equal to this is delta O this can be written as delta Hi over delta Xi So, this is semi-discrete equation in terms of time. Suppose we want to use an explicit scheme, the simplest one would be our explicit Euler method. So, let's use explicit Euler method for time integration of 4. So, then what we will get? Look at rho V I at time instant n plus 1 is equal to rho V I at time n plus delta t times del Hi at n divided by del Xi minus delta Pn over delta Xi. Now, in this equation we have only one problem, Hi, which contains our convective term and diffusive term taken together, that is explicitly known in terms of the flow variables at time level t is equal to Tn, but same thing we cannot say about pressure. This Pn would usually be unknown. Now, the velocity field which we have calculated, that must satisfy continuity equation. So, this V I n plus 1 must satisfy continuity equation. So, let us take divergence of equation 5. So, what do we get? Del over del Xi of rho V I n plus 1 del over del Xi of rho V I at n delta t times del over del Xi of del Hi n over del Xi so Hi, so we will have here only Hi minus del over del Xi of del Pn over del Xi. Now, remember we have to satisfy the continuity equation. The velocity field must satisfy it at time Tn plus 1. So, that the first term, the term on LHS must vanish. The velocity field which was available there at time t is equal to Tn, that would also satisfy our continuity equation. So, this term also vanishes. So, these two terms vanish for continuity. So, thereafter what we are left with is del over del of Xi delta Pn over delta Xi is equal to del Hi over del Xi. So, this is what is our pressure Poisson equation. So now we have got all the tools which we require for explicit time integration. If you wanted to use the formula given by this equation 5, in equation 5, to obtain the value at time level n plus 1, we needed the evaluation of hi and this del p n over del xi. Hi can be computed in terms of the values at time level n, and Pn can be computed by solution of a pressure Poisson equation. So, the steps are clear now. First, let us evaluate this Hi, then obtain numerical divergence of Hi, use that as a source term for the pressure Poisson equation, solve for the pressure Poisson equation, obtain the pressure field, take its gradient and use it in our explicit formula for the velocity components to get our flow field. Now, let us summarize these steps. Starting with the velocity field Vn at time Tn, compute Hn, which contains the advective and viscous terms of momentum equation, and find out its divergence that we need as a source term for the pressure Poisson equation. The next is solve the pressure Poisson equation to obtain Pn, and once we know Pn, then we know this explicit formula in which we substitute for del p n by del xi and h at n, and that gives us the velocity field at time level Tn plus 1. Now, we have demonstrated this explicit integration with forward Euler scheme. The process would be almost same if you want to use a higher order schemes such as Adams-Basforth or less explicit Runge-Kutta methods. Now, the advantage of the explicit scheme is obvious. They are very simple to implement. The velocity component evaluation requires just a straightforward algebraic formula. So, velocity field is obtained explicitly in terms of the values at previous time step, provided we know the pressure. So, we have to solve only one system of linear equations which results from pressure Poisson equation. So, the implementation of this explicit solver is pretty straightforward. And remember here, the only system of equations which we have to solve, that is our pressure Poisson equation. So, that is that makes this step the most demanding step in explicit Navier-Stokes solver, and because of this reason, the solution of pressure Poisson equation is still one of the most challenging research areas at the moment. People are trying to develop fast and faster what typically call fast Poisson solvers, which can be used for large scale flow simulations. The disadvantage is that we need to have very small time step, that is mandated by the stability requirements. So, these methods are unsuitable for steady state or slow transient problems, wherein large time steps would be preferred to reach the steady state very quickly. And for these steady state problems or their slow transient problems, we would prefer implicit or semi implicit solvers. So, let us have a brief look at the implicit schemes. Now, this implicit time integration methods are normally used for solution of steady state or slow transient flows, for which we need to employ large time steps. But there is one small problem here. We have to solve a set of coupled nonlinear equations. We have got momentum equations which are coupled nonlinear equations, and we have the Poisson equation for pressure as again in terms of the products of the velocity components which are unknown. So, we have got a coupled system of nonlinear equations which must be solved simultaneously using a Newton-Raphson type iterative scheme. And in our this iterative process, the results of the preceding time step are known to us. So, they are used as initial guess in the iterative process. Very often what we do is we linearize these equations, use the value of the previous time step in that linearization process. So, we get a system of linear equations, solve them, get the updated value, use that updated value in the quasi-linearization process to get a next system of linear equations, solve them, and continue this iterative process until we are satisfied with the convergence at a given time step. So, this quasi-linearization is very often used in conjunction with implicit time integration schemes. And the solution scheme is very obvious here, that we have to take the velocity and pressure field at time level n as a starting guess for the values at time t n plus 1, solve the coupled nonlinear system of equations, momentum equation and pressure Poisson equation simultaneously to obtain the velocity and pressure field at the new time level. This pressure Poisson equation we already derived yesterday in the previous lecture. Okay, so that completes the algorithm part. And remember that these implicit time integration schemes, they are extremely demanding in terms of computation time and memory requirements, as we need to solve a very large nonlinear system at each time step. So, as I mentioned earlier, we would usually go for what we call a quasi-linearization, so that we need to solve only a sequence of linear systems, especially for steady state problems. We will see a few specialized schemes which are based on this quasi-linearization approach in a set of schemes which are termed as pressure correction based schemes in the next lecture.